The cosmos is meant to be a realm of unwavering order, a stage for the inexorable march of gravity where nothing dares disrupt its measured tempo. Yet, in November of the year 2025, an unprecedented event shattered this illusion. An interstellar interloper, designated 3 Atlas and scarcely larger than a colossal mountain, commenced an inexplicable acceleration. There were no visible engine firings, no gaseous plumes, no discernible cause whatsoever. Concurrently, the Sun unleashed a tempest of ferocious solar flares, causing Earth's protective magnetic shield to quiver violently. Amidst this cosmic upheaval, scientist Stefan Burns uttered a somber prognostium. A significant surge is imminent. 2 disparate occurrences, converging at a singular juncture. Were these mere happenstance or a meticulously orchestrated sequence? Comets are not known for such predictable comportment. They falter, they pirouette, they diminish. But this entity defies such erratic behavior. Its movement is fluid, exact, almost as if preordained. Thus, this evening we embark on a silent pursuit of its trajectory through the inky expanse to confront a question that could fundamentally alter our perception of the natural world. If 3 Atlas is indeed a comet, as they would have us believe, then why is it behaving as though it were a spacecraft that has just reawakened to its directive? Should this enigma continue to captivate you as it has me, please ensure you engage the like button and subscribe to remain abreast of every development as this unfolds in real time. Share in the comments section your location, the current time there, and whether you feel we are receiving the complete narrative regarding these groundbreaking revelations. And if you are inclined to support the expansion of this community, I urge you to share this video on X, Facebook, Reddit, or even within your personal group chats. Your engagement is the very reason we can continue to pursue stories of this magnitude. Therefore, my sincere gratitude for your unwavering support. Part 1 delves into a significant discovery: the perplexing propulsion of 3 Atlas. Something is amiss in the frigid reaches of our solar system, a truth that few are yet willing to voice aloud. In November of 2025, celestial observers charting the course of the interstellar object 3 Atlas, also identified as C2025N1, detected an anomaly that defied established physics. This celestial body was not merely adhering to its predicted path, it was actively increasing its velocity in a manner inexplicable by gravitational forces alone. The data originated from NASA's Jet Propulsion Laboratory Horizon system, the sophisticated computational framework responsible for the precise tracking of everything from orbital satellites to near-Earth asteroids. These figures painted a narrative that unsettled the scientific community. The acceleration was dissected into 3 distinct vectors, labeled A1, A2, and A3, signifying the directional forces influencing the object's motion. A1, representing the radial component, movement either towards or away from the Sun, registered approximately 1.662 multiplied by 10 to the -6th power astronomical units per day squared. A2, the tangential component, propulsion along the object's trajectory, was recorded at roughly 7.089089 multiplied by 10 to the -7th power astronomical units per day squared. A3, the out-of-plane component, indicated a value of precisely 0, a mathematically impossible null. To grasp the significance of this finding, it is imperative to understand its context. When astronomers observe comets, they frequently document non-gravitational acceleration. Comets, being icy bodies, sublimate when exposed to solar radiation, expelling gas and dust into the void. This expulsion generates a propulsive force, akin to a leaking pressure vessel navigating the vacuum. These nascent jets invariably divert the comet from its purely gravitational trajectory. However, the expulsion of material from a rotating, irregularly shaped mass of ice and rock is inherently a chaotic process. Jets erupt in multiple directions, the nucleus tumbles, its surface is uneven, resulting in propulsive forces acting across all 3 spatial dimensions: radial, tangential, and critically, out of plane. 3 Atlas exhibited no such disarray. Its propulsion was confined entirely within the orbital plane, as though it were programmed to exert force solely in 2 dimensions, completely disregarding the third. Over a period of approximately 20 days, this sustained acceleration resulted in a velocity alteration of about 60 meters per second. This is not a subtle effect. It represents tangible, continuous thrust that should invariably leave observable traces. Yet, investigators searching for such evidence found nothing. No newly emerged object was detected. No trailing tail extended behind the entity. No distinct jets were resolved in high-resolution imaging. The object presented itself, for all practical purposes, as inert. Its apparent magnitude remained consistently between 14.7 and 14.9, displaying minimal fluctuation. It was not brightening like a comet roused by proximity to the sun. It was not fracturing or shedding discernible matter. It simply accelerated silently and with precision within a single plane. Envision observing a vessel gliding across a body of water devoid of any visible means of propulsion. No engine, no sails, no oars. The water in its wake shows no disturbance, yet the vessel steadily gains speed, traversing in a perfectly straight line as if guided by unseen tracks. Such a spectacle would undoubtedly prompt profound questions. The central inquiry concerning 3 Atlas is this: if it is merely a comet, why is it exhibiting characteristics of a spacecraft? The implications of this phenomenon extend far beyond a solitary, enigmatic rock drifting through our solar system. If conventional explanations falter, if we exhaust every conceivable mechanism that the fields of physics and chemistry can propose, we are left with 2 stark possibilities. Either we are witnessing an extraordinary natural phenomenon currently beyond our scientific comprehension, or we are observing something deliberately engineered. Both scenarios necessitate a re-evaluation of our understanding of interstellar objects. Both carry ramifications that permeate our comprehension of solar system dynamics, the fundamental nature of matter traversing interstellar space, and indeed, the disquieting question of whether humanity is alone. Around the same temporal juncture that 3 Atlas began its anomalous acceleration, geophysicist Stefan Burns issued a grave warning. He asserted that Earth was entering a period of heightened energetic activity. Solar flares were intensifying, geomagnetic storms were assaulting the planet's magnetic field, and seismic events were occurring with unusual frequency. Burns highlighted a convergence of factors: a recurring 28-day cycle of coronal holes on the Sun, the peak of the torrid meteor shower in early November, a supermoon event on November 5th, and impending planetary alignments. His thesis suggested that these were not isolated incidents, but rather components of a grander pattern, an escalating crescendo of cosmic energy manifesting across multiple celestial systems. The convergence of these timings creates a striking coincidence. Here we have an interstellar visitor exhibiting inexplicable behavior at the precise moment our star and planet appear to be escalating their energetic output. Coincidences, naturally, occur. The universe is vast, and events frequently intersect without any causal link. However, when confronting anomalies, coincidences begin to resemble clues, hinting at a broader context we may be overlooking. This presentation will meticulously examine the evidence, the anomalies, and the hypotheses, both natural and unconventional. We will scrutinize the data that causes scientists trepidation. We will explore the ramifications of attempting to reconcile 3 Atlas with our existing models of cometary behavior, observing how these models strain under the pressure. We will consider alternative explanations that verge on the realm of science fiction but may hold the kernel of scientific fact. We will contextualize this object within the framework of other interstellar visitors, the ambient energetic environment of our solar system, and the cutting-edge discoveries that are reshaping our understanding of small celestial bodies and fundamental physics. And ultimately, we will pose the question that, as yet, few dare to articulate too loudly. What if this object is more than just a comet? What if it is signifying something far more profound? Time marker, 0.5 seconds. Part 2 addresses the fundamental nature of the A3=0 condition. Let us first delineate how comets are expected to behave erratically. Understanding the norm will illuminate why 3 Atlas deviates so starkly. As a comet approaches the Sun, solar radiation heats its surface, causing ice to sublimate directly from solid to gaseous form, bypassing the liquid state entirely. This process generates jets of vapor that carry dust particles along. These jets escape through fissures or vents on the nucleus. The direction of the resulting thrust vector varies depending on the location of these vents and the orientation of the nucleus at any given moment. The nucleus is almost certainly in a state of rotation, tumbling through space along a complex axis. As it spins, different vents are exposed to solar heating at different times. The consequence is a thrust vector that constantly shifts in three-dimensional space, propelling the comet radially, tangentially, and out of its orbital plane. The majority of comets exhibit significant out-of-plane acceleration. The A3 component is seldom zero because natural processes are inherently chaotic. Surface characteristics vary, rotational states are complex, and the timing of vent activation is influenced by thermal conductivity, subsurface structure, and the distribution of volatile compounds, all of which differ across the nucleus's surface. Thrust can be directed upwards, downwards, sideways, or in combinations thereof that evolve as the comet rotates and as solar heating intensity changes with distance. Orbital modelers who track these celestial bodies routinely incorporate all 3 components, as the observational data mandates it. Statistical analyses of cometary non-gravitational forces clearly demonstrate this. When examining dozens or hundreds of comets, the distribution of A3 values spans a broad spectrum. Some comets display minimal out-of-plane components, while others exhibit substantial ones. However, a value of absolute 0 is exceptionally rare. It is conceivable to achieve an A3 value close to 0 if the observational period is brief or the acceleration is weak. But when sustained acceleration occurs over weeks and the observational baseline is robust, an A3 value of 0 becomes a definitive statement. It signifies that the propulsion is constrained, disciplined, and aligned within a single plane. 3 Atlas yielded an A3 value of 0 within the margin of error for the JPL Horizon's orbital calculations. The residuals, the minute discrepancies between the object's predicted and actual observed positions, did not necessitate any out-of-plane component. The orbital solution remained consistent without it. This is not an artifact of insufficient data. The observational coverage encompassed multiple sites over an extended period, and the astrometric precision was high. Had there been any meaningful out-of-plane thrust, the orbital fit would have detected it. Therefore, what does it signify when an object accelerates for 20 days without deviating from its orbital plane? It implies that the mechanism generating this thrust is either remarkably stable or exceptionally controlled. For natural outgassing to achieve this, the nucleus would require a specific configuration where jets are exclusively directed within the orbital plane, never perpendicular to it. Imagine a nucleus with a precise geometric form, oriented in a particular fashion, with vents positioned such that their combined thrust cancels any perpendicular component while augmenting the radial and tangential forces. While not impossible, this scenario demands a level of geometric precision rarely observed in nature. One proposed hypothesis involves uniform vent distribution. If the nucleus possesses numerous small vents dispersed evenly across its surface, and if these vents expel material at similar rates, the individual thrust vectors might converge to produce a net force residing within the orbital plane. However, this hinges on a prerequisite of symmetry. It demands that the nucleus's axis of rotation align in a highly specific manner with the orbital plane. Furthermore, it requires that the surface composition and thermal properties be sufficiently homogeneous to prevent any single hemisphere from dominating the outgassing process. Each of these conditions, individually, represents a significant constraint. Collectively, they begin to appear highly contrived. Another hypothesis centers on an unusual volatile composition. Perhaps 3 Atlas is exceptionally rich in substances such as carbon monoxide or nitrogen. These volatiles sublimate at high velocities but carry minimal dust. High-velocity gas jets generate greater thrust per unit of mass expelled, which could account for the observed acceleration without a visible coma. Nevertheless, this explanation does not resolve the issue of planar confinement. Gas jets emanating from a rotating body should still possess out-of-plane components, unless the rotational axis and vent geometry conspire in a precise manner. A third possibility involves micro-outgassing. Minuscule jets ejecting particles at high speeds, but in quantities too small to be resolved by current telescopic capabilities. This could potentially explain the absence of a discernible coma, but it does not address the A3 anomaly. Even microjets should vary in direction as the nucleus rotates, producing some out-of-plane thrust unless the system exhibits extraordinary symmetry. The condition of zero out-of-plane thrust opens the door to more unconventional interpretations. If one were designing a propulsion system for a small spacecraft, the priority would be to maintain the thrust vector aligned with the trajectory. Wasting propellant by expelling it perpendicular to the intended motion would be inefficient. Engines would be fired within the orbital plane to adjust speed and direction optimally. A perfectly planar thrust profile is precisely what one would expect from controlled propulsion. This does not definitively confirm 3 Atlas as a spacecraft. Rather, it suggests that the observed propulsive signature is more consistent with active control than with passive, chaotic outgassing. It is a piece of evidence that fits more snugly into one conceptual framework than another, even if that framework presents an uncomfortable picture. Consider the alternative. If 3 Atlas is naturally venting, then we are witnessing a celestial coincidence of geometry, composition, rotational state, and timing so exact that it mimics artificial behavior. While nature can be surprising, it rarely presents such a neat and orderly phenomenon. If there is no observable venting or coma, then what is the source of this propulsion? Part 3 examines the observational paradox of an absent coma or tail. Telescopes across the globe have been meticulously observing 3 Atlas. Both ground-based observatories and orbital assets, alongside professional and amateur astronomers, have directed their instruments towards this interstellar visitor as it traverses the inner solar system. They have measured its luminosity, tracked its position, and diligently searched for any indicators of activity. What they have encountered is an object of remarkable quiescence. The apparent magnitude of 3 Atlas has remained stable, fluctuating around 14.7 to 14.9. For perspective, this is far too dim to be perceived by the unaided eye, but well within the capabilities of moderately sized telescopes. The brightness did not exhibit the characteristic variations typically observed from a comet awakening as it nears perihelion. There were no sudden flares, no outbursts, and no gradual increase corresponding to heightened sublimation rates. Its light curve more closely resembled that of an asteroid than an active comet. When a comet undergoes significant outgassing, the consequences are usually apparent. A coma develops, a diffuse cloud of gas and dust encircling the nucleus. This coma can extend for thousands, even hundreds of thousands of kilometers, glowing as sunlight scatters off its particles and as molecules fluoresce under ultraviolet radiation. Depending on the angle of observation, a tail becomes visible, swept back by the solar wind and radiation pressure. Distinct jets may also be observed, narrow streams of material erupting from specific vents on the nucleus. The object's visual appearance transforms, its brightness fluctuates, and its morphology becomes complex. 3 Atlas displayed none of these phenomena. High-resolution imagery failed to resolve any substantial coma, no discernible tail stretched behind the object, and no jets were visible in the publicly released data. The object appeared point-like, more akin to a barren rock than an outgassing comet. Spectroscopic analysis, where available, should have revealed emission lines from volatile gases such as water vapor, carbon monoxide, carbon dioxide, or cyanogen. These spectral signatures serve as unique identifiers, indicating which substances are sublimating from the surface. However, reports suggest minimal or absent gaseous signatures, implying that the object was not venting material. Let us now consider the quantitative implications. To achieve a velocity change of 60 meters per second over a 20-day period, 3 Atlas must have been subjected to a propulsive force. If this force originates from outgassing, we can estimate the mass that would need to be expelled and at what velocity. The rocket equation dictates that the change in velocity equals the exhaust velocity multiplied by the natural logarithm of the ratio of initial mass to final mass. Given the object's modest size and uncertain mass, this calculation becomes inherently speculative, but we can establish order of magnitude estimates. Let us assume the nucleus possesses a mass of several million kilograms, perhaps 10 million for the sake of argument. To achieve a delta V of 60 meters per second, with gas expelled at a velocity of a few hundred meters per second, typical for water vapor or carbon monoxide sublimation, a substantial fraction of its mass would need to be lost. Let us posit a few percent, translating to hundreds of thousands of kilograms of material ejected into space. Where did this expelled matter go? A few 100,000 kilograms of gas and dust should readily produce a visible coma. Dust particles are highly effective at scattering sunlight. Even if the rate of dust production were low, the accumulation over 20 days should have formed a detectable envelope. The fact that observers have not detected this presents a significant challenge. Perhaps the ratio of dust to gas is exceptionally low. It is conceivable that 3 Atlas is expelling pure gas with virtually no dust. While gas alone is difficult to detect visually, its presence should be evident through spectral emissions. Yet, early reports do not confirm strong gaseous emissions. Another possibility is that the venting occurs in extremely minute quantities spread across a vast surface area, causing the gas to disperse instantaneously and preventing the formation of a dense coma. Microjets, individually imperceptible, might be responsible for generating the thrust. This is a plausible scenario, but it necessitates a highly specific surface structure and venting regime. Most comets do not operate in this manner. They tend to concentrate activity in a limited number of vents, producing discrete jets rather than a diffuse haze. An alternative explanation might involve the ejection of exceptionally small particles, nanoparticles, or even molecules that do not efficiently scatter visible light. Smaller particles tend to scatter more effectively in ultraviolet and infrared wavelengths. If 3 Atlas is expelling material optimized for invisibility and optical wavelengths, it could be accelerating without any visible indication. However, this hypothesis introduces a very specific particle size distribution and composition, adding another layer of complexity to the natural explanation. The paradox intensifies. Acceleration implies a force, and a force implies mass ejection if we are discussing rocket-like propulsion. Mass ejection should generate observable signatures, yet these signatures are absent. Either the ejection is occurring in a manner we do not yet fully comprehend, or the force is not derived from mass ejection at all. If venting is absent or invisible, what else could be generating the thrust? Part 3 scrutinizes natural outgassing hypotheses under duress. Let us give natural explanations their due consideration. Let us examine each hypothesis with earnestness. Scientific inquiry proceeds by testing concepts against empirical evidence, and it is incumbent upon us to exhaust all mundane possibilities before embracing the extraordinary. Hypothesis 1. Uniform vent distribution. Imagine the nucleus of 3 Atlas as a roughly spherical body dotted with numerous small vents. Solar heating penetrates the surface, causing the ice beneath each vent to sublimate and escape. If these vents are evenly dispersed and expel material at comparable rates, the individual thrust vectors might combine to produce a net force that coincidentally lies within the orbital plane. The operative word here is coincidentally. This scenario requires that the nucleus's axis of rotation be oriented such that the distribution of active vents, averaged over time, yields no net perpendicular component. For this to be feasible, the nucleus must possess a specific rotational state, with its axis of rotation oriented perpendicular to, or nearly perpendicular to, the orbital plane. This would ensure that as it spins, vents on all sides are activated symmetrically. The surface composition must be sufficiently uniform to prevent any single hemisphere from dominating the outgassing process. Thermal conductivity must be consistent, precluding the development of localized hotspots with intensified venting. While each of these conditions is plausible in isolation, their collective occurrence represents a highly improbable confluence. Most comets lack such precise symmetry. Their surfaces are uneven, their shapes irregular, and their spin axes are tilted at arbitrary angles. The probability of encountering an object that coincidentally fulfills all these criteria is exceedingly low. Hypothesis 2. Unusual volatile composition. It is possible that 3 Atlas is exceptionally rich in highly volatile ices, such as carbon monoxide, carbon dioxide, or molecular nitrogen. These substances sublimate at lower temperatures and higher velocities compared to water ice. High-velocity ejection results in greater thrust for each kilogram of mass lost. If the dust content is minimal, this would lead to acceleration without a prominent coma. Expelling only gas without significant dust would render the process optically inconspicuous. However, even pure gas plumes should be detectable through sensitive spectroscopy, and early reports do not indicate strong gas emissions. Furthermore, the fundamental issue of planar confinement remains unresolved by this hypothesis alone. Gas jets emanating from a rotating body should still exhibit out-of-plane components unless the rotational axis and vent geometry are precisely aligned to counteract this. Carbon monoxide readily vaporizes even at considerable distances from the Sun, potentially accounting for the consistent propulsion over an extensive trajectory. The underlying physics are sound. Carbon monoxide has been identified in other comets and is known to generate thrust. However, this theory still encounters the A3 anomaly. Without precise alignment of volatile distribution and vent configuration, thrust would be exerted in all 3 spatial dimensions. Additionally, if carbon monoxide is the driving force behind the acceleration, spectral indicators of its emission should be detectable. Observers should be able to pick them up. If not, it implies either observational limitations or insufficient quantities of the substance. The third hypothesis posits micro-outgassing and mass shedding. Rather than substantial jets, envision the surface releasing material gradually through innumerable minute vents or direct vaporization across the entire Sun-facing hemisphere. While the rate of gas and dust generation per unit of surface area is low, integrated over the entire expanse and spanning weeks, it accumulates to a propulsion sufficient to account for the observed acceleration. Due to the diffuse nature of the ejection, a concentrated coma is not formed, only a faint veil imperceptible to current instruments. This scenario necessitates exceptionally fine-grained activity. The surface must possess a porosity that permits gas to permeate and escape universally, not confined to specific openings. The thermal wave induced by solar heating must penetrate the subsurface effectively, driving vaporization beneath the surface layer. The escaping gas must carry minimal dust, or dust so fine as to be invisible. It represents a delicate equilibrium. Excessive dust results in a coma, while insufficient gas fails to generate adequate thrust. Achieving this precise balance and maintaining it for 20 days demands a level of regulation that nature typically does not exhibit. All 3 proposed explanations face a shared impediment: observational limitations. The absence of a discernible coma and tail is not a minor inconvenience for these models. It forms their central conflict. Every mechanism posited to explain the thrust predicts observable outcomes, and these outcomes are conspicuously absent. We can introduce supplementary explanations, hypothesize specific conditions, and meticulously adjust parameters. But at a certain juncture, we must question whether we are distorting the explanation to fit the data or faithfully following the data's direction. Thermal modeling exacerbates the issue. A diminutive celestial body within the inner solar system is subjected to intense solar heating on its illuminated side. This energy fuels vaporization. The rate of mass loss is contingent upon the quantity of volatiles, the thermal conductivity, the rotational period, and the surface albedo. For 3I Atlas to sustain continuous thrust for 20 days without evident outgassing, all these variables must coalesce in a highly specific manner. The nucleus must be sufficiently small to avoid substantial gravitational influence that impedes efficient ejection, yet massive enough to contain adequate volatiles for sustained propulsion. It must rotate rapidly enough to distribute solar heating evenly, but not so fast that centrifugal forces become dominant. Its surface characteristics must preclude dust entrainment while facilitating gas escape. Each additional stipulation constricts the range of possible parameters. What began as a broad category of natural phenomena, comets venting when heated, has narrowed to a highly specific challenge. None of these hypotheses are inherently impossible. Nature often surprises us, but they are under considerable strain, and this strain is significant. Therefore, if natural hypotheses prove inadequate, let us direct our attention to more unconventional possibilities. Part 5 delves into artificial or exotic hypotheses, including light sails, propulsion, or uncharted physics. We now enter speculative territory, and it is crucial to acknowledge this from the outset. What follows are conceptualizations, not established truths. These are scenarios that align with some observed aspects but lack definitive substantiation. Science requires extraordinary evidence for extraordinary claims, and we have not yet reached that threshold. However, given the anomaly we are confronting, these ideas cannot be summarily dismissed. Hypothesis 1 proposes a slender reflective sail propelled by radiation pressure. Envision a structure of exceedingly low mass and expansive surface area, essentially a mirror tumbling through space. Sunlight striking its surface is reflected, transferring momentum. The force generated is minuscule but applied continuously over days or weeks, accumulating over time. The critical factor is its areal mass density, the mass per unit area. For a sail to achieve noticeable acceleration under solar radiation, it must be exceptionally thin, perhaps a few micrometers or less, with high reflectivity. Let us perform a quantitative assessment. Solar radiation pressure at 1 astronomical unit from the Sun approximates 4.5 micronewtons per square meter. If 3I Atlas possesses an effective area of, say, a few square kilometers and a total mass of a few thousand kilograms, its acceleration could reach the observed 10 to the power of -6 astronomical units per day squared. The precise figures depend on reflectivity, orientation, and solar distance. However, the order of magnitude is consistent. A sail would naturally generate thrust aligned with the Sun's direction, predominantly radial. However, if the sail is inclined relative to the Sun, the thrust vector will rotate. Depending on its orientation and spin, components both radial and tangential could be produced, consistent with the A1 and A2 values. The A3 equals 0 condition is met if the sail's rotational axis or orientation remains within the orbital plane, a plausible scenario for a thin structure subjected to torques from radiation pressure and potentially interstellar magnetic fields. The absence of a coma is perfectly explained. A sail does not outgas. It reflects. It would appear as a faint, steady point of light, precisely as observed. The primary challenge lies in explaining the origin of such a structure. Natural processes do not construct sails. Ice fragments or thin dust sheets might momentarily resemble sails, but maintaining their coherence and orientation for weeks is difficult to rationalize. If 3I Atlas is a sail, it is likely an artifact of design. Hypothesis 2 suggests controlled propulsion. Assume 3I Atlas is equipped with a propulsion system, be it chemical, electric, nuclear, or of a more esoteric nature. This system would operate periodically or continuously to modify the object's trajectory. The thrust would be intentionally directed, accounting for the precise planar confinement of its motion. The lack of visible exhaust could indicate the use of a propellant that is not readily detectable, or an exhaust velocity so high that the plume disperses instantaneously. For a chemical rocket, propellant mass and an engine would be required. To achieve a delta V of 60 meters per second with a typical exhaust velocity of a few kilometers per second, a minor fraction of the total mass would be expended. A small spacecraft could carry sufficient fuel. Electric propulsion, such as ion drives, operates at significantly higher exhaust velocities, necessitating even less propellant. The trade-off is power. An energy source is required, such as solar panels or a nuclear battery, to operate the engine. This immediately raises the question of motive. If 3I Atlas is a spacecraft, what is its mission? Why would it engage its propulsion midway through the solar system? Perhaps it is executing a course correction, aiming for a specific destination. It might be decelerating after an interstellar journey. Alternatively, the thrust could be part of a data collection or communication protocol that remains unknown to us. Or it could be experiencing a malfunction, firing its thrusters unintentionally. Without understanding the intent, we can only speculate. However, the observed pattern of thrust appears deliberate, not random. Hypothesis 3 explores unknown physics. What if the acceleration originates from a mechanism not yet characterized by science? Examples include dark matter drag, where 3I Atlas traverses a region of concentrated dark matter particles exerting a subtle force, or electromagnetic interactions, where the object carries an electrical charge and interacts with the solar wind's magnetic field in an unexpected manner, or boundary effects within the solar system, such as a property of the heliosphere or the galactic cosmic ray wind that influences motion in unmodeled ways. These concepts reside at the cutting edge of scientific understanding. Dark matter itself remains poorly understood. Its existence is inferred from gravitational effects on galaxies, but its properties and interactions are still mysterious. If dark matter can exert a drag force on ordinary matter under certain conditions, then objects passing through regions of higher dark matter density might experience such forces. The magnitude required to explain 3I Atlas's acceleration far exceeds current dark matter models, but these models are inherently incomplete. Electromagnetic scenarios presuppose that 3I Atlas possesses a significant electrical charge or magnetic moment. Interstellar space is replete with charged particles, including protons, electrons, and heavier ions. If an object is electrically charged, these particles exert forces upon it. The solar wind also carries a magnetic field. Interactions between moving charges and magnetic fields generate forces. Could this account for the observed thrust? The issue lies in scale. The solar wind pressure and magnetic forces acting on a small body are typically orders of magnitude weaker than the observed acceleration. This would necessitate extraordinary conditions or unknown amplification mechanisms. Comparing these exotic hypotheses against the available data, the light sail scenario emerges as the best fit. It accounts for the planar thrust, the absence of a coma, and the consistent brightness. Controlled propulsion aligns almost as well, but it introduces complexities regarding intent and origin. Unknown physics represents the most speculative category, conceptually plausible but lacking a well-defined mechanism. Each hypothesis demands further observational evidence. For a sail, measurements of albedo and reflectivity, seeking unusually high values, would be beneficial. For a propulsion system, we would look for directional changes or velocity adjustments consistent with deliberate maneuvers. For unknown physics, theoretical advancements and independent observations of similar phenomena elsewhere would be required. The extraordinary nature of these claims cannot be overstated. To suggest that 3I Atlas might be a sail or a spacecraft is not a casual assertion. It is a hypothesis born from anomalies that defy conventional explanations. We are not asserting proof. Rather, we are stating that the data makes us uncomfortable. And when data elicits discomfort, all possibilities must be explored, even those that sound like science fiction. Having examined the anomaly and the hypotheses, let us broaden our perspective. How does this fit within the larger context of interstellar objects, solar system energy dynamics, and less apparent factors? Part 6. Interstellar Objects and Comparative Behavior. Interstellar objects are transient visitors, originating from beyond our solar system. They formed around other stars, were expelled from their home systems through gravitational interactions, and traverse the galaxy for millions or billions of years before entering ours. Until recently, they were purely theoretical constructs. Their existence was inferred from probabilistic considerations. However, none had been directly observed. Then, in October 2017, the Pan-STARRS telescope in Hawaii detected an object moving at exceptionally high velocity, too fast to be gravitationally bound to the Sun. Astronomers rapidly mobilized to observe it before it receded beyond reach. They named it Oumuamua, a Hawaiian term meaning scout, or first distant messenger. Oumuamua presented peculiarities. Its trajectory was hyperbolic, confirming its interstellar provenance. Its shape appeared highly elongated, possibly 10 times longer than its width, resembling a cigar or a pancake tumbling end over end. Its light curve exhibited periodic variations in brightness, consistent with this elongated form. As it moved away from the Sun, it displayed non-gravitational acceleration, a subtle yet significant outward push not attributable to gravity alone. Some researchers proposed outgassing, despite the absence of a visible coma or tail. Others suggested more speculative explanations, including the possibility that it was a light sail, either naturally occurring or artificial. The debate surrounding Oumuamua became intense. The majority of scientists favored natural explanations, arguing that unusual outgassing or an asymmetric shape could account for the observed acceleration without a visible coma. A minority, including Harvard astronomer Avi Loeb, contended that the data was more congruent with a thin, reflective object propelled by radiation pressure, potentially an artifact. This controversy underscored the limited understanding of interstellar objects and how swiftly assumptions can be challenged when data deviates from expectations. In August 2019, a second interstellar visitor arrived. This object, designated Borisov, differed from Oumuamua. Borisov presented as a typical comet, complete with a prominent coma and tail as it approached the Sun. Spectroscopic analysis revealed familiar volatiles, including water, carbon monoxide, and cyanogen. Its behavior aligned with astronomical expectations for comets, albeit one originating outside our solar system. Borisov provided reassurance to the scientific community that most interstellar objects are likely ordinary, and Oumuamua may have been an exceptional case. Now, with the appearance of 3I Atlas, we have an object that is neither Oumuamua nor Borisov. It shares characteristics with both, but fits perfectly into neither category. Like Oumuamua, it exhibits non-gravitational acceleration without visible outgassing, raising questions about the source of its propulsion. Like Borisov, it follows a trajectory indicative of a cometary path, entering the inner solar system and experiencing solar heating. However, its thrust profile, specifically its confined planar motion, distinguishes it. Oumuamua's acceleration had radial and tangential components, but also uncertainties that might have masked out-of-plane effects. Borisov's outgassing was clearly three-dimensional, characteristic of an active comet. 3I Atlas occupies an intermediate position, anomalous but in a unique way. This prompts the question, is 3I Atlas merely another interstellar visitor exhibiting unusual behavior, or is it a fundamentally different type of object? If we are observing three distinct interstellar objects within less than a decade, each with unique characteristics, what does this imply about the population as a whole? Extrapolating from such a small sample is fraught with peril. We are unaware of potential selection biases. Brighter objects are more easily detected. Highly reflective or unusually active objects might be overrepresented. We are, in essence, casting a small net into a vast ocean of possibilities. Consider detection bias. Current surveys typically identify interstellar objects when they are relatively close and luminous. Fainter, smaller, or less active objects may elude detection. If a population of low-mass, sail-like structures exists drifting between stars, we might only detect them when they are near perihelion and become visible due to sunlight. The same logic applies to small, inert bodies that register only as faint points of light. The population of interstellar objects could be far more diverse than our 3 data points suggest. Imagine a scenario where 3i Atlas is part of a fleet, a swarm of sails or probes launched by an advanced civilization long ago to explore the galaxy. Most would pass through solar systems unnoticed, but occasionally one might be detected because its proximity to a star causes it to brighten. This is speculative, bordering on the fantastical, but it is not contradicted by the data. If intelligent civilizations exist and have mastered interstellar travel or communication, deploying lightweight probes would be a logical strategy. Thin sails propelled by starlight, carrying minimal payloads, could traverse immense distances over millennia. Alternatively, perhaps 3i Atlas is a fragment, a piece of an engineered structure that fractured eons ago. It could be discarded debris from an alien system drifting on galactic currents, or it might be entirely natural, a type of object we have yet to characterize due to a lack of opportunities for close-up study of interstellar material. Perhaps comets originating from other stellar systems form in environments distinct from our own, with compositions or structures that result in unusual venting regimes. Comparing the behavior of interstellar objects frames the question of whether 3i Atlas is an outlier or an indicator of a changing pattern. If every interstellar object we discover exhibits anomalies, then anomalies become the norm, and we must adjust our expectations accordingly. If 3i Atlas stands alone, it becomes a puzzle demanding resolution. At present, with only 3 examples, a definitive conclusion is elusive, but the emerging pattern is suggestive. Interstellar objects do not behave like native solar system bodies. They surprise us. They challenge our assumptions, and each new discovery expands the scope of what we consider possible. Having looked outward to other interstellar objects, let us now turn inward to the energy environment of our own solar system and how it might influence such behavior. Part 7. The Solar System Energy Environment. Solar flares, coronal mass ejections, and geomagnetic activity. The Sun is not a static, quiescent sphere of light. It is a dynamic nuclear furnace governed by a powerful magnetic dynamo, with its activity fluctuating on timescales ranging from minutes to decades. Currently, in late 2025, the Sun is intensifying its activity. Solar Cycle 25, which commenced in late 2019, is approaching its peak phase. The period of maximum activity characterized by an increase in sunspots, frequent solar flares, and coronal mass ejections that expel plasma into space. Solar flares are sudden releases of magnetic energy stored within the Sun's atmosphere. They manifest as brilliant bursts of light in extreme ultraviolet and X-ray wavelengths, releasing energy equivalent to millions of hydrogen bombs. Flares are categorized by their X-ray intensity: A-class, B-class, C-class, M-class, and X-class, with each successive class representing a 10-fold increase in power. M-class flares are of moderate strength and can cause brief radio blackouts on Earth's sunlit side. X-class flares are the most powerful, capable of triggering radiation storms and disrupting satellite electronics. Coronal mass ejections, or CMEs, are even more dramatic events. These are colossal eruptions of plasma and magnetic field from the Sun's corona, propelled into interplanetary space at speeds ranging from hundreds to thousands of kilometers per second. When a CME impacts Earth's magnetosphere, it compresses the magnetic field, inducing electrical currents in the ionosphere and on the ground. Geomagnetic storms ensue, producing auroras at high latitudes, disrupting power grids, degrading GPS signals, and exposing astronauts to increased radiation. In 2025, observers have recorded multiple M-class and X-class flares, along with several significant CMEs. The frequency of these events is escalating as the solar cycle progresses towards its maximum, anticipated around 2025 or 2026. High-speed solar wind streams emanating from coronal holes have bombarded Earth's magnetosphere, resulting in recurrent geomagnetic disturbances on an approximate 27-day cycle, corresponding to the Sun's rotational period as viewed from Earth. So, what is the relevance of this to 3I Atlas? Small bodies within the solar system are not immune to the Sun's energetic influence. Solar radiation and the solar wind affect them in multiple ways. Radiation pressure exerts a force on their surfaces, a mechanism previously discussed in the context of light sails. Charged particles within the solar wind can sputter atoms from exposed surfaces, eroding material atom by atom. Photoelectron emission, where ultraviolet light dislodges electrons from the surface, can electrically charge the object, creating electric fields that interact with the solar wind's magnetic field. For icy bodies, solar heating drives sublimation, the primary process responsible for cometary activity. However, heightened solar output during flares or CMEs could temporarily increase heating rates, triggering bursts of outgassing. Alternatively, if the object is charged, interactions with the solar wind plasma might generate forces, augmenting or modifying the thrust from radiation pressure or outgassing. These mechanisms are subtle, typically producing effects far smaller than the observed acceleration of 3I Atlas. But in principle, they could contribute. The temporal coincidence is noteworthy. 3I Atlas's anomalous acceleration was detected in November 2025 during a period of elevated solar activity. Stefan Burns highlighted this same time frame, pointing to a confluence of factors: the 28-day recurrence of coronal holes, peak Taurid meteor activity, a supermoon, and what he termed a significant wave of energetic disturbances affecting Earth. Is this connection genuine or coincidental? Let us quantify the forces involved. Solar wind pressure at 1 astronomical unit is approximately 1 to 6 nanopascals, depending on whether one is within slow or fast solar wind. For an object spanning a square kilometer in its cross-sectional area, the forces involved would be on the order of millitons. Consider the immense force required to achieve an acceleration equivalent to that of 3I Atlas. If an object possessed a mass in the millions of kilograms, forces ranging from mere newtons to tens of thousands of times the pressure exerted by solar wind alone would be necessary. This clearly indicates that solar wind cannot be the primary propulsion mechanism. Radiation pressure, at approximately 4.5 micropascals at 1 astronomical unit, is significantly more potent. However, even this force falls short unless the object exhibits exceptional characteristics, such as the minimal aerial mass of a solar sail. While an increase in solar output during solar flares could temporarily boost radiation pressure by a few %, it would be insufficient to account for sustained acceleration over a period of 20 days. What about electromagnetic interactions? Should 3I Atlas carry a substantial electrical charge, perhaps acquired through photoemission or interaction with interstellar plasma prior to entering our solar system, it could engage with the magnetic field of the Sun, which is embedded within the solar wind. A charged particle moving within a magnetic field experiences the Lorentz force, acting perpendicularly to both its velocity and the field. Depending on the magnitude of the charge and the field strength, this interaction could generate forces. Nevertheless, the resultant forces would still be minimal. The magnetic field of the solar wind at 1 astronomical unit is approximately 5 nanoteslas. To generate significant force, one would require enormous electrical charges, far exceeding what photoemission or standard charging mechanisms can produce. It is conceivable that unknown couplings or amplification mechanisms are at play, where solar activity instigates responses within the object's surface or interior that have not yet been incorporated into our models. For instance, if 3I Atlas possesses a highly conductive surface, rapidly fluctuating magnetic fields from coronal mass ejections could induce eddy currents, creating magnetic moments that interact with the solar wind. This is highly speculative and would necessitate exotic material properties, but it remains a conceptual possibility. A more probable connection might be indirect. Solar activity impacts the entire heliosphere, the vast bubble of solar wind and magnetic field enveloping our solar system. Fluctuations in solar output alter the density, temperature, and magnetic configuration of this environment. Small bodies traversing this region might encounter different conditions than they would during periods of solar minimum. If 3I Atlas is venting material, heightened solar heating or variations in ambient pressure could modulate the rate or direction of this venting. If it functions as a sail, shifts in radiation pressure or magnetic torques could alter its orientation, thereby affecting its thrust. The core challenge lies in the fact that none of these proposed mechanisms adequately explain the observed data. The acceleration is consistent and planar, rather than sporadic or reactive to solar flares. There is no discernible correlation between flare events and any changes in 3I Atlas's trajectory. The connection remains speculative, a tantalizing coincidence rather than a definitively proven cause. However, coincidences do tend to accumulate. Burns himself had warned of a significant energetic event, and 3 Atlas began exhibiting unusual behavior. The Sun is currently more active, and an interstellar visitor is engaging in unexplained actions. It is possible that these events are unrelated. Conversely, they might be interconnected. The universe is a complex web of interactions, many of which we are only beginning to comprehend. Forces and fields permeate space, linking distant celestial bodies through subtle interactions. When multiple systems display anomalies concurrently, it warrants an investigation into whether they share a common underlying cause. If our Sun and heliosphere are indeed playing a role, could Earth itself be integrated into a larger energetic phenomenon? This leads us into discussions of seismic activity and the big wave narrative. Part 8 delves into seismic activity, Earth-based effects, and the big wave narrative. Stefan Burns may not be a universally recognized name, but his pronouncements carry considerable weight among those who monitor geophysical phenomena and space weather. In late 2025, Burns issued a grave warning. Earth was entering a period of intensified energetic activity, a confluence he termed the big wave. His reasoning is based on the simultaneous alignment of several factors, each capable of influencing terrestrial geological and atmospheric systems. Firstly, the 28-day recurrent cycle of coronal holes. Coronal holes are areas in the Sun's atmosphere where the magnetic field extends into space, permitting high-speed solar wind to escape. These holes can persist for weeks or months, and as the Sun completes a rotation approximately every 27 days, the same hole can repeatedly face Earth, directing pulses of fast-moving solar wind towards us. Each pulse compresses Earth's magnetosphere, inducing geomagnetic storms. Burns observed that in late 2025, a particularly active coronal hole was generating powerful recurring disturbances, subjecting Earth's magnetic field to intense pressure roughly every 4 weeks. Secondly, the torrid meteor stream. Earth passes through the torrid stream twice annually, once in late October and early November, and again in late June and early July. This stream is composed of debris originating from Comet Encke and potentially fragments of larger celestial bodies that disintegrated millennia ago. In early November 2025, Earth traversed the densest portion of this stream, encountering a greater number of meteors and possibly larger particles than usual. Some researchers have hypothesized that meteor impacts, even minor ones, could potentially trigger atmospheric or seismic events, although concrete evidence for this remains scarce. Thirdly, the supermoon on November 5, 2025. A supermoon occurs when a full moon coincides with the moon's closest orbital approach to Earth. During these celestial events, the moon's gravitational influence on Earth intensifies, leading to increased tidal forces. Tides not only affect the oceans but also the solid crust of the Earth, causing measurable deformation. Certain studies suggest that these tidal stresses might influence the timing of earthquakes, particularly for fault lines already in a state of near failure. Fourthly, planetary alignments. Burns referenced upcoming alignments involving Jupiter, Saturn, and other planets. Configurations that are purported to concentrate gravitational influences on both the Sun and Earth. While astrologers have long asserted the significance of such alignments, mainstream scientific opinion remains skeptical. The gravitational forces exerted by distant planets on Earth are exceedingly minor when compared to the tidal forces generated by the Moon and the Sun. Any resultant effect would likely be lost within the background noise. Burns synthesized these elements, contending that their simultaneous occurrence created a temporal window of heightened energetic activity, manifesting as increased solar flares, geomagnetic storms, and, crucially, seismic events. He cited recent earthquakes, a magnitude 6+ event in Kamchatka, Russia, another in Afghanistan, and tremors in other locations, as evidence that Earth's crust was reacting to this convergence. The scientific community's reception to such assertions is, at best, mixed. The proposition that solar or geomagnetic activity can trigger earthquakes has been the subject of decades of research, yielding inconclusive results. Some studies have identified weak correlations between geomagnetic storms and shallow seismicity, particularly in volcanic regions where magma movement might be influenced by electrical currents or pressure variations. Conversely, other studies have found no correlation, attributing any apparent patterns to statistical anomalies or publication bias. The prevailing consensus is that while external forces, such as tides, can exert a slight modulating influence on earthquake timing, they do not cause earthquakes themselves. Tectonic stress accumulates over years or centuries, and external triggers, at best, nudge already primed faults towards rupture. The fundamental challenge with a big wave narrative lies in discerning a genuine signal from mere noise. Earthquakes occur continuously. Magnitude 6 events happen hundreds of times globally each year. Solar flares and geomagnetic storms are common during periods of solar maximum. Supermoons occur approximately every 1 to 2 years. Meteor showers are predictable occurrences. When one searches for patterns within noisy data, it is often possible to find them, even if they are purely coincidental. Humans are inherently pattern-seeking beings, and our brains are adept at identifying connections that may not objectively exist. Nevertheless, outright dismissal of Burns's claims would be premature. Scientific progress is driven by the investigation of anomalies and the rigorous testing of hypotheses. If a genuine physical mechanism links solar activity to seismicity, its discovery necessitates thorough investigation, not reflexive skepticism. Certain researchers are actively exploring how geomagnetic disturbances might influence rock conductivity, generate piezoelectric effects in rocks, or alter fluid pressure within fault zones. These are subtle effects, challenging to measure and even more difficult to definitively prove, but they are not inherently impossible. Now, let us consider how this connects to 3I Atlas. Burns did not explicitly link his big wave concept to the interstellar object. However, the temporal proximity invites speculation. If Earth is experiencing an energetic convergence, could similar processes be affecting objects traversing the solar system? Might amplified solar wind or heliospheric disturbances influence 3I Atlas's observed behavior? One perspective suggests that both phenomena might stem from a common source. It is possible that the solar system is currently passing through a region of interstellar space characterized by a higher density of charged particles or dust, which could simultaneously affect Earth's magnetosphere and smaller bodies like 3I Atlas. The solar system travels through the galaxy at an approximate speed of 250 kilometers per second, and the local interstellar medium is not uniform. We periodically enter clouds of gas and dust, regions with varying densities and temperatures. If we have recently entered a denser region, this could amplify solar wind interactions, increase meteor influx, and potentially exert forces on small celestial bodies. Another avenue of exploration involves electromagnetic interactions. Both Earth's magnetosphere and a potentially charged 3I Atlas interact with the heliospheric magnetic field. Variations in the Sun's output alter the structure of this field. It is conceivable that the same magnetic fluctuations that trigger geomagnetic storms on Earth also affect 3I Atlas, inducing torques or forces that modify its trajectory. This hypothesis remains highly speculative and would require mechanisms that are currently beyond our understanding. A third perspective is purely observational. The big wave might represent a cognitive framework, a narrative that consolidates unrelated events due to their concurrent occurrence. 3I Atlas's anomaly, Earth's seismic activity, and solar storms could be entirely independent phenomena, and the attempt to connect them might be an instance of apophenia, the perception of meaningful patterns within random data. Science mandates that we rigorously test this possibility. Burns's assertions do not align with mainstream scientific thought, and many of his specific predictions or proposed causal links lack substantial empirical support. However, the temporal clustering of events is undeniable. Multiple systems are exhibiting activity within the same time frame. Whether this is mere coincidence, a shared underlying cause, or a manifestation of interconnected processes remains an open question. The big wave narrative compels us to consider the solar system as an integrated system, rather than a collection of isolated phenomena. Beyond the solar and seismic narratives, there exist hidden data controversies and complex social dynamics within the research community. Let us delve deeper into these aspects. Part 9 examines hidden angles and controversies within the scientific community. Science is ideally an objective pursuit, guided by data and logic, free from bias and political influence. In reality, the process is considerably more complex. Scientists are human beings with egos, career aspirations, funding pressures, and intricate social dynamics that shape which topics are investigated, which findings are published, and which theories gain acceptance. The unfolding story of 3 Atlas is not confined to telescopes and equations. It also plays out in conference rooms, peer review panels, and online forums where ideas collide and reputations are either forged or fractured. Let us begin with the issue of data transparency, specifically concerning the non-gravitational parameters for 3I Atlas. The A1, A2, and A3 values originate from NASA's Jet Propulsion Laboratory Horizons system. Horizons is a publicly accessible tool, allowing anyone to query orbital elements and make predictions. However, the underlying data, the astrometric observations that inform the orbital fit, are derived from a multitude of sources, including professional observatories, amateur astronomers, and sky surveys. Not all of this data is immediately available to the public. Some observations are considered proprietary, retained by survey teams until their findings are formally published. Other data is shared through the Minor Planet Center, an international clearinghouse for asteroid and comet data, but its quality and completeness can vary. Independent researchers have taken the available data and conducted their own orbital fits, disseminating their results on forums, preprint servers, and social media platforms. Some of these analyses concur with JPL's solution, while others show minor deviations, indicating a sensitivity to the specific observations included and the weighting assigned to residuals. Orbital mechanics is a precise field, but it is not entirely immune to interpretation. The process of selecting which data points to trust, how to manage outliers, and which model to employ for non-gravitational forces all involve subjective judgment calls. Different analysts arrive at different conclusions, leading to shifts in the results. This presents a challenge when an individual claims that 3 Atlas exhibits zero out-of-plane acceleration. Are they reporting a robust finding or an artifact of their particular dataset and fitting procedure? Peer review is intended to identify such issues. Yet much of the discourse surrounding 3I Atlas is occurring outside of formal academic channels, proliferating on platforms like Twitter, YouTube, Reddit, and various blogs. Ideas spread rapidly, while the peer review process moves at a glacial pace. By the time official papers are published, the prevailing narrative may have already been established. Furthermore, there is the question of anomalies in color and reflectivity. Certain observers have reported that 3I Atlas appears bluer than typical comets or asteroids, with a spectrum that suggests high reflectivity or an unusual surface composition. Blue spectral characteristics can be indicative of fresh ice, a lack of dust, or the presence of specific minerals. In the context of the light sail hypothesis, a high albedo and blue coloration would lend support to the notion of a reflective surface. However, accurate color measurement is a complex undertaking. It is contingent upon the phase angle, the angle formed between the sun, the object, and the observer. As this angle fluctuates, the brightness and perceived color of the reflected light also shift. Observers must meticulously correct for these variations, and these corrections rely on models that may not be applicable to unusual celestial objects. Instrument calibration is another critical factor. Different telescopes, detectors, and filters each introduce systematic errors. Ambient sky glow, atmospheric absorption, and interference from nearby stars contribute additional noise. Consequently, when a claim emerges that 3I Atlas exhibits an anomalous blue hue, it is pertinent to inquire, compared to what, using which instruments, and with what corrections applied. If such a claim is based on a limited number of data points from a single observer, it is suggestive but not conclusive. If multiple independent teams utilizing different instruments corroborate the observation, the claim gains significant strength. To date, the publicly available evidence remains sparse, and the scientific community is proceeding with caution. Speculative hypotheses face considerable hurdles within academia. Proposing that 3I Atlas might be an artificial object or a light sail typically elicits skepticism and at times, outright dismissal. The peer review system is inherently conservative, favoring explanations that align with established scientific frameworks. Papers that posit novel physics or extraordinary claims demand exceptional evidence, and reviewers subject them to stringent scrutiny. While this rigor is appropriate, it can also inadvertently stifle innovation. If every unconventional idea is rejected before a comprehensive body of evidence can be gathered, there is a risk of overlooking genuine discoveries. There is also a discernible social dimension to this phenomenon. Researchers who champion exotic explanations risk damaging their professional reputations. Mainstream scientists may deliberately distance themselves, apprehensive of being associated with fringe theories. Funding agencies tend to favor safer, more predictable projects that promise incremental advancements rather than paradigm-shifting breakthroughs. Career progression, including tenure and grant success, is contingent upon publishing in respected journals, which, in turn, often prioritize conventional research. This dynamic fosters a bias toward naturalistic explanations, even when the available data strains to accommodate them. Conversely, contrarian researchers who embrace speculative ideas may become professionally isolated, forming their own communities where unconventional thinking is lauded, but critical scrutiny might diminish. Echo chambers can emerge, where consensus solidifies and dissenting voices are disregarded. This dynamic operates in both directions, the mainstream dismissing the fringe, and the fringe dismissing the mainstream. Social media platforms exacerbate these tendencies. A single assertion about 3I Atlas, even if supported by preliminary data, can achieve widespread dissemination before undergoing rigorous vetting. YouTube channels, blogs, and podcasts capitalize on anomalies, crafting narratives that attract audiences but may not accurately reflect scientific consensus. Mainstream scientists often respond, sometimes dismissively, thereby creating a perceived chasm between official science and independent researchers. The public observes this unfolding dynamic, often uncertain about whom to trust. To what extent might biases within the scientific community or publication biases influence our interpretation of 3I Atlas's anomaly? While quantifying this impact is challenging, its effects are palpable. If researchers unconsciously favor naturalistic explanations because they are more readily publishable, they may not pursue exotic hypotheses with the same level of dedication. Conversely, if contrarian researchers overemphasize anomalies because they align with their existing worldview, they might neglect mundane explanations that could prove accurate. Ideally, science possesses an inherent self-correcting mechanism through replication, debate, and the accumulation of evidence. However, this process is inherently slow and imperfect. The paramount consideration is intellectual humility, the capacity to acknowledge the limits of our knowledge, which is often more challenging than it appears. Scientists are trained to provide definitive answers, and uncertainty can be perceived as failure. Yet, 3 Atlas presents a genuinely perplexing case. The available data does not readily fit into established categories. The most scientifically sound approach involves acknowledging this uncertainty, exploring a multiplicity of hypotheses without premature commitment, and patiently awaiting the acquisition of more comprehensive data. Having examined the contextual background and the associated controversies, we shall now proceed to map the landscape of hypotheses and assess which hold greater promise and which are likely to be unproductive avenues of inquiry. Part 10 presents a hypothesis matrix, mapping possibilities and probabilities. Let us delineate the field of potential explanations. We are confronted with several competing hypotheses aiming to account for 3I Atlas's observed behavior. Each hypothesis posits different preconditions, makes distinct predictions, and aligns with the available evidence to varying degrees. The objective at this juncture is not to definitively declare a winner, but rather to map the spectrum of possibilities and identify the crucial observations that would most decisively alter our confidence in each hypothesis. Hypothesis: natural comet outgassing with uniform vents. Required conditions for this hypothesis include a cometary nucleus possessing numerous small, evenly distributed vents, a spin axis oriented perpendicular to the orbital plane, ensuring symmetrical venting, uniform surface composition and thermal properties, and sufficient volatile content to sustain thrust over a 20-day period. Evidence supporting this hypothesis includes the object's hyperbolic trajectory, indicative of an interstellar origin, and the well-established phenomenon of ice sublimation in comets. Evidence against this hypothesis encompasses the absence of a visible coma or tail, a stable brightness inconsistent with vigorous outgassing, and the requirement of extraordinary geometric precision to achieve zero out-of-plane acceleration. Key unknowns remain the nucleus's size, shape, spin state, surface composition, and the distribution of volatiles within it. Plausibility rating: moderate but strained. This represents the default assumption for comets, yet the lack of visible activity and the precise planar thrust are difficult to reconcile. Hypothesis: unusual volatile composition, rich in carbon monoxide or nitrogen. Required conditions involve a high abundance of supervolatiles that sublimate at low temperatures and high velocities, a low dust-to-gas ratio that minimizes visible coma formation, and a vent geometry that somehow confines the thrust to the orbital plane. Supporting evidence includes the possibility that interstellar objects originating from different environmental conditions might possess exotic compositions and supervolatiles capable of generating high thrust per unit mass. Evidence against this hypothesis includes the expectation of spectroscopic detection of carbon monoxide or carbon dioxide emissions, which have not been clearly reported, and the persistent challenge of confining thrust to the orbital plane. Key unknowns pertain to detailed spectroscopic results and the precise composition of the nucleus. Plausibility rating: moderate but constrained by observational gaps. Supervolatiles are plausible, but the absence of gas detections is a significant concern. Hypothesis: radiation pressure acting upon a thin, low-mass, sail-like structure. Essential requirements encompass an exceptionally low aerial mass, potentially a few grams per square meter, exceptional reflectivity approaching 100%, an orientation angled towards the sun to generate both radial and tangential propulsive forces, and the maintenance of structural integrity for periods spanning weeks. Corroborating evidence includes a flawless alignment with the absence of a coma or tail, as reflective surfaces do not expel gas. A planar propulsive force naturally arising from a thin structure constrained by rotational forces. Consistent luminosity assuming stable reflectivity, and radiation pressure forces that scale appropriately at the observed solar distances. Counterarguments arise from the necessity of either artificial or exceedingly infrequent natural formation and the lack of direct measurements confirming high albedo or reflectivity. However, crucial undetermined factors remain the precise albedo and reflectivity measurements, analysis of the phase curve, and detailed structural imaging. The plausibility rating is low to moderate, yet the fit is compelling. Should the object known as Oumuamua possess sail-like characteristics, this theory gains considerable strength. The primary obstacle lies in substantiating the existence of such properties. A competing hypothesis posits controlled propulsion from an engineered spacecraft. This scenario necessitates an onboard propulsion system with a propellant or energy reservoir, deliberate application of thrust for trajectory adjustments or deceleration, minimal discernible exhaust or exhaust too faint for detection, and purposeful activity indicating intelligence or programming. Supporting evidence includes the precise planar thrust consistent with controlled firings, sustained acceleration observed over 20 days aligning with the capabilities of an efficient propulsion system, and the absence of a coma, which is indicative of non-chemical propulsion methods like electric drives. However, the extraordinary nature of this claim demands equally extraordinary proof, and there is ambiguity regarding the motive for thrusting mid-trajectory, with no other indications of artificiality such as radio emissions or geometric structure. Key unknowns include the detection of any signals or emissions, trajectory modifications suggesting maneuvers, and higher resolution imaging. The plausibility rating is highly speculative but cannot be dismissed. This represents the most extraordinary hypothesis and requires the most rigorous substantiation. A further hypothesis involves exotic physics, such as dark matter interactions or electromagnetic phenomena. This scenario requires passage through a region of concentrated dark matter or charged particles, a novel coupling between the object and the interstellar or heliospheric medium, and effects that produce forces on the order of 10 to the -6th astronomical units per day squared, sustained over weeks. Supporting evidence includes theoretical possibility if new physics exists, and unexplained acceleration that invites novel mechanisms. Evidence against this hypothesis includes the absence of a theoretical framework predicting such effects at the observed magnitudes, no independent evidence of anomalous dark matter or fields in this region, and forces derived from known exotic mechanisms being far too weak. Key unknowns involve measurements of the local space environment and advancements in dark matter physics theories. The plausibility rating is very low, though conceptually open, representing a frontier wildcard. Unlikely but not impossible. For each proposed hypothesis, specific critical observations exist that would decisively alter probability assessments. The detection of a coma or jets would strongly favor natural outgassing. Measuring very high albedo, approaching 100%, would support the sail hypothesis. Observing trajectory changes that correlate with deliberate maneuvers would indicate propulsion. The detection of unusual emissions or spectral signatures might lend credence to exotic physics or reveal the object's composition. High-resolution imaging revealing structured geometry would hint at artificiality. The presented data matrix highlights our areas of uncertainty, underscoring a desperate need for enhanced observational data. Spectroscopic analysis is crucial for detecting or ruling out gas emissions. Photometry across multiple wavelengths is needed to constrain albedo and reflectivity. Astrometry over an extended observational arc will refine non-gravitational parameters. If feasible, radar or resolved imaging would allow for direct observation of the nucleus itself. Each measurement serves to narrow the range of viable hypotheses. Presently, we exist in a state of productive uncertainty. Multiple hypotheses remain plausible, and none can be definitively excluded. This situation is unsettling but scientifically honest. Science flourishes in such environments where data challenges existing assumptions and compels deeper contemplation. The ensuing 12 months will be pivotal as further observations become available and theoretical models are refined. In our concluding section, we will broaden our perspective by examining related scientific narratives from 2025 that may inform our understanding and expand the context. Part 11. Recent Breakthroughs in Artificial Intelligence and Astrophysical Surveying, 2025. Astronomy is currently inundated with data, a fortunate predicament. The next generation of celestial surveys, notably the Vera C. Rubin Observatory's Legacy Survey of Space and Time, abbreviated LSST, promises to capture imagery of the entire observable sky every few nights, generating tens of terabytes of data daily. Traditional analytical methods, which involve human examination of images or the execution of pre-programmed algorithms, are insufficient to keep pace. This is where artificial intelligence enters the picture. In 2025, several research teams announced significant advancements in AI-driven anomaly detection for astronomical surveys. Machine learning algorithms, particularly deep neural networks, have been trained on extensive datasets encompassing known celestial objects such as stars, galaxies, asteroids, and comets. Once proficiently trained, these networks can meticulously examine new observations, flagging any entities that deviate from established patterns. An object exhibiting anomalous motion, displaying unusual fluctuations in brightness, or possessing spectral characteristics inconsistent with known classifications will be marked for further investigation. A noteworthy instance involved a collaborative effort utilizing precursor data from the LSST. Their algorithm successfully identified several faint-moving objects that had been previously overlooked by conventional detection pipelines. Some of these were subsequently identified as distant trans-Neptunian objects, icy bodies situated beyond Neptune's orbit. Others were near-Earth asteroids on unconventional trajectories, and one, intriguingly, exhibited signs of non-gravitational acceleration reminiscent of that observed in Oumuamua. The AI flagged this object because its trajectory deviated from a purely gravitational path, and subsequent analysis confirmed propulsive components that did not align with typical cometary gas expulsion. These techniques operate by learning what constitutes normal behavior, subsequently identifying outliers among moving celestial bodies. Normal behavior is defined as adherence to Keplerian orbits, paths governed by gravitational forces. Deviations signal either measurement errors or genuine physical phenomena, such as gas venting, collisions, or, in more speculative scenarios, propulsion. The algorithms are capable of discerning these deviations even in data that is too noisy or subtle for human analysts to detect. When applied to Oumuamua, AI tools could potentially assist in detecting faint coma or tail features that are invisible to standard processing. Machine learning can enhance images, extracting valuable signals from noise by recognizing patterns in light scattering or the appearance of faint structures. If a whisper-thin coma surrounds Oumuamua, an AI trained on images of active comets might detect it where human observers would not. AI also improves astrometry, the precise measurement of object positions. By analyzing thousands of reference stars and accounting for systematic errors in telescope pointing, atmospheric distortions, and detector artifacts, algorithms can refine positional accuracy to sub-pixel levels. Enhanced astrometry leads to tighter constraints on orbital parameters and non-gravitational forces. The A2 and A3 values for Oumuamua could be refined with improved measurements, potentially clarifying whether A3 is truly zero or merely very small. Beyond detection and measurement, AI is being employed for classification. Based on an object's spectrum, light curve, or orbital characteristics, algorithms can predict its type: asteroid, comet, trans-Neptunian object, or interstellar visitor. These classifications rely on patterns learned from thousands of examples. When an object does not conform to any established class, it is flagged as anomalous. Oumuamua would likely trigger such a classifier due to its combination of features from multiple classes. Interstellar origin, similar to Oumuamua, potential venting like comets, yet exhibiting planar thrust and lacking a coma, unlike either. The implications are substantial. As survey sensitivity increases, the number of detected anomalies will grow. We may discover dozens of objects exhibiting peculiar behavior, necessitating an expansion of our classification system. If several of these exhibit sail-like properties, The sail hypothesis for Oumuamua would become less extraordinary. If many demonstrate planar thrust, we would need to comprehend the natural mechanisms responsible for this pattern. Conversely, if Oumuamua remains unique, its anomalous nature becomes more pronounced. There is also the issue of false positives. AI algorithms can be misled, misinterpreting noise as genuine signals or exhibiting overfitting to training data. Anomalies flagged by AI require human verification, spectroscopic follow-up, and multi-wavelength observations. The process from detection to confirmation involves multiple stages, each presenting potential for error. However, the sheer volume of data renders AI indispensable. We cannot afford to have humans review every single image. We require intelligent filters that direct our attention to the most significant cases. Speculation. What if AI uncovers numerous sail-like or unusually moving objects in archival data? These could be objects that passed unnoticed years ago, suggesting a population of such entities and altering our interpretation of Oumuamua. Instead of a solitary anomalous visitor, it might belong to a category, whether natural or artificial. The existence of a category implies a formation or deployment mechanism, something that generates these objects in quantity. Alternatively, if AI surveys the sky for years and finds no other object resembling Oumuamua, that finding is equally informative. It suggests that such objects are rare, either because they are naturally uncommon or because they are artifacts from a sparse population of probes. Rarity does not prove artificiality, but it amplifies the mystery. The challenge moving forward is managing expectations. Increased data will yield more anomalies, but also more noise and potential misinterpretations. The interplay between human intuition and machine pattern recognition will define the next era of astronomy. Oumuamua is situated at the intersection of these trends, presenting a puzzle that demands both cutting-edge tools and careful human judgment for its resolution. How might improved detection and analysis methods alter our understanding of Oumuamua? Within the next 1 to 2 years, we will likely have more precise orbital solutions, refined non-gravitational parameters, deeper images to search for faint features, and comparisons with newly discovered similar objects. Each piece of information brings us closer to an answer. Part 12. Advances in Solar Physics, Major Coronal Mass Ejection, Flare Event. This year, 2025. On March 19, 2025, the Sun unleashed a significant outburst. An X-3.7 class flare erupted from active region 3962, a vast aggregation of sunspots near the solar equator. The flare reached its peak intensity at 1423 Coordinated Universal Time, inundating Earth's sunlit hemisphere with X-rays and extreme ultraviolet radiation. Radio operators reported widespread communication disruptions on high-frequency bands as the ionosphere absorbed the sudden influx of energy. However, the flare was merely the initial event. 30 minutes later, coronagraph imagery from the Solar and Heliospheric Observatory, SOHO, revealed a massive coronal mass ejection propelling outward from the flare site. The CME carried billions of tons of magnetized plasma, expanding into a cloud hundreds of times larger than Earth. Its initial velocity was recorded at over 2,000 kilometers per second, swift enough to reach Earth in less than 20 hours. When the CME impacted Earth's magnetosphere on March 20th at 1100 Universal Time, the effect was dramatic. Solar wind pressure surged, compressing the magnetosphere and triggering a severe G4 geomagnetic storm. Auroras became visible across skies as far south as the Mediterranean and the northern United States. Power grid operators reported induced currents stressing transformers. Satellite operators maneuvered spacecraft to avoid the most intense radiation, and astronauts aboard the International Space Station retreated to shielded modules. This event was not an isolated incident. It was one of several major flares and CMEs in 2025, but it vividly exemplified the Sun's power during solar maximum. These occurrences provide a natural laboratory for investigating how solar output influences the space environment and the objects within it. CMEs and flares alter conditions throughout the heliosphere. Particle fluxes increase, bombarding planets, moons, and small bodies with protons, electrons, and heavier ions. These particles carry energy, eroding surfaces, sputtering atoms into space, and electrically charging exposed materials. For icy bodies like comets, intensified particle bombardment can modify sublimation rates or generate electric fields on their surfaces. Radiation pressure also fluctuates. While the sun's luminosity and visible light vary by less than 0.1% during flares, ultraviolet and X-ray output can increase by orders of magnitude. Objects with high albedo and significant reflectivity at ultraviolet wavelengths experience stronger radiation pressure during flares, potentially generating temporary variations in thrust. The solar wind's magnetic field, typically a few nanoteslas at 1 astronomical unit, can surge tenfold during CME passages. Rapidly changing magnetic fields induce electrical currents in conductive materials. If Oumuamua possesses metallic components or conductive ice, these currents could generate magnetic fields that interact with the solar wind, producing forces or torques. Could the March 19th event, or similar occurrences, have triggered or amplified Oumuamua's anomalous acceleration? The timing does not perfectly align. Oumuamua's non-gravitational acceleration was detected in November, months after the March event. But solar activity remained elevated throughout 2025, with multiple M and X-class flares and recurring CMEs. If a connection exists, it would likely stem from sustained environmental changes rather than a single event. One possibility involves cumulative effects. Repeated CMEs and high-speed streams erode surfaces over time. If Oumuamua entered the inner solar system during a period of high solar activity, its surface might have been altered, exposing fresh volatiles or modifying its reflective properties. This could, in turn, affect its response to solar heating or radiation pressure. Another perspective involves plasma interactions. The solar wind is a plasma, a gas composed of charged particles. Objects traversing plasma can develop bow shocks, regions where the plasma flow is disturbed. If Oumuamua is electrically charged, its interaction with the plasma could be complex, potentially generating forces. During CME passages, plasma density and velocity spike, intensifying these interactions. However, the forces involved are typically modest, significantly weaker than the observed acceleration. Theoretical research in 2025 has explored how extreme solar events impact small bodies. One study modeled dust ejection from asteroids during CME impacts, concluding that electrostatic forces can levitate dust particles from the surface, creating transient clouds. If Oumuamua is shedding dust electrostatically rather than through sublimation, this might account for the absence of a visible coma. The dust disperses too rapidly to form a concentrated cloud. However, this mechanism produces intermittent rather than sustained thrust. The most probable conclusion is that advancements in solar physics expand our comprehension of the boundary conditions governing small body behavior, but do not fully elucidate Oumuamua's nature. Solar events modify the environment, but the object's response is contingent upon its intrinsic properties: composition, structure, electrical charge, and reflectivity. Without knowing these properties, it is impossible to definitively ascertain whether solar activity plays a role. Speculative inquiry. What if Oumuamua passed through a transient solar wind enhancement, a dense, slow-moving structure ejected from the sun, and the interaction generated drag or thrust that persisted for days? Solar wind structures can extend for tens of millions of kilometers, and an object traversing one might experience sustained forces. This is a considerable extrapolation, as the forces involved are weak, but when combined with other mechanisms, it might contribute. Solar physics reveals that the heliosphere is a dynamic, not static, environment. Conditions fluctuate based on location, time, and solar activity levels. Oumuamua's journey through this environment is shaped by these variations. Understanding solar influences helps delineate the realm of possibility, even if it does not fully resolve the mystery. Part 13. New findings in small body physics. Sample return or Comet mission results. 2025. In September 2025, the Japan Aerospace Exploration Agency, JAXA, announced a remarkable new set of findings from the extended analysis of samples returned by its Hayabusa 2 mission to asteroid Ryugu. Although the spacecraft had delivered its precious cargo back to Earth in late 2020, detailed laboratory study of the microscopic grains has continued for years. The new results, published in Nature Astronomy, may have fundamentally altered scientists' understanding of outgassing, surface evolution, and non-gravitational acceleration in small celestial bodies. At first assessment, Ryugu appeared well understood. A dark, carbonaceous near-Earth asteroid, highly porous and loosely aggregated, more of a rubble pile than a solid rock. However, the 2025 findings unveiled deeper insights. Ryugu's grains are permeated with microscopic fractures, nanovoids, and channels, forming a sponge-like internal structure. Embedded within are hydrated minerals and trace organic compounds, indicative of past aqueous alteration. What surprised scientists, however, was the behavior of these grains under vacuum and heat. When subjected to simulated sunlight in laboratory conditions, the samples consistently released gases, despite appearing dry. This process is not explosive venting, as depicted in the classic image of cometary jets erupting from a nucleus. Instead, it is diffusive outgassing. Trapped volatiles, including water molecules, carbon dioxide, nitrogen, and other trace gases, slowly migrate outwards through a complex network of pores. The gas release is gentle, uniform, and sustained, generating a continuous, low-level propulsive force. Researchers estimated that on an asteroid-sized body, this process could produce non-gravitational acceleration detectable over days or weeks, yet without forming a visible coma or tail. This is where Oumuamua becomes relevant. If the interstellar object Oumuamua possesses a similarly porous and volatile-rich structure, this mechanism could provide a natural explanation for its mysterious sustained in-plane acceleration, the one reported by NASA's JPL Horizon system in November 2025. Unlike typical comets that vent through localized jets, producing visible plumes and asymmetric thrust, a diffusively venting body would exert thrust uniformly across its surface, resulting in a subtle, smooth acceleration, precisely as observed. This could also account for the absence of a detectable coma or tail. The gas might be escaping too uniformly and too faintly to scatter light or carry dust in detectable quantities. If the primary volatiles are weak emitters, such as nitrogen, argon, or carbon monoxide, then even the most sensitive spectroscopic surveys might miss them. In essence, Oumuamua could be venting invisibly. However, this elegant theory still presents challenges. The A30 condition in the JPL orbital solution, signifying no out-of-plane acceleration, remains a persistent issue. Even with diffuse outgassing, a rotating body should exhibit fluctuations in thrust direction unless its spin axis coincidentally aligns with its orbital plane, a rare occurrence. Therefore, while the Hayabusa 2 findings broaden the spectrum of potential natural behaviors, they do not definitively resolve the enigma. The geometry remains a critical factor, and thus far, the numerical data does not perfectly align. Nonetheless, the implications of Ryugu's gentle outgassing are profound. It suggests that the boundary between asteroids and comets is more indistinct than previously believed. A celestial body can appear inert and rocky, yet still exhibit subliminal activity under solar heating. Over extended periods, such subtle outflows could even alter an asteroid's trajectory or, within an interstellar context, mimic controlled motion. Further elaborating, the European Space Agency's Comet interceptor mission, slated for deployment in the latter part of the 2020s, released a series of preparatory research papers in the year 2025. These documents detailed its strategic approaches for investigating pristine long-period or interstellar visitors. Within this collection, a simulation study delved into the phenomenon of microjets. narrow, sporadic expulsions of gas and dust. These are too faint to be detected from Earth, but possess the potential to generate a measurable propulsive force. Based on these simulations, microjets could impart net accelerations in the range of 1.06 to 10 to the 7th astronomical units per day squared, a magnitude consistent with the observed behavior of 3I Atlas. Critically, these jets could activate intermittently, influenced by solar radiation and surface temperatures. However, their averaged effect could approximate a nearly constant acceleration, provided the object's rotation and orbital orientation were favorably aligned. From an earthly perspective, this would manifest as a smooth acceleration confined to the orbital plane, the very signature currently perplexing astronomers. The Comet interceptor studies also highlighted that the surface's microtexture, the configuration of cracks, fissures, and granular inclines, can significantly impact how solar energy is absorbed and re-emitted. A rough, porous surface can amplify localized heating and sublimation, even at considerable distances from the Sun. Coupled with our understanding of Ryugu's porous composition, this paints a picture of small celestial bodies as actively evolving surfaces, continuously reshaped by subtle physical processes invisible to telescopic observation. Concurrently, complementary findings from NASA's OSIRIS-REx mission, which successfully returned samples from asteroid Bennu in the year 2023, reinforce this evolving understanding. Analyses published in 2024 and 2025 revealed that Bennu's regolith is similarly fragile and porous, exhibiting a mechanical strength lower than anticipated, resembling compacted powder more than solid rock. Such a structure could facilitate the outward diffusion of deeply embedded volatiles more readily than previously theorized. OSIRIS-REx also documented instances of particle ejection during its close proximity operations around Bennu, where small fragments spontaneously detached from the surface without any identifiable vent. Collectively, the Hayabusa 2 and OSIRIS-REx missions have presented a revised perspective. Small celestial bodies are not merely inert lumps of rock, but intricate semi-active aggregates capable of producing detectable accelerations without conspicuous visual indicators. For 3I Atlas, this provides a compelling analogy, though not definitive proof, suggesting its behavior might align with a spectrum of natural processes that we are only beginning to quantify. Naturally, speculation is rife. Could the microstructure of an interstellar object differ even more dramatically? Having traversed interstellar space for millions of years, subjected to cosmic ray bombardment and frozen beyond the heliopause, its surface might have acquired unique reactive properties. As such a body re-enters the solar system, sudden solar heating could trigger the release of trapped volatiles in unforeseen ways, akin to activating a long-dormant power source. Some researchers have posited that interstellar material could even contain novel ices or amorphous carbon compositions not found in typical comets, which might sublimate differently under solar irradiation. Others venture further. Within more speculative discussions, the consistent acceleration and directional stability of 3I Atlas have reignited comparisons to Oumuamua, whose own non-gravitational acceleration in the year 2017 sparked debates concerning light sails, artificial probes, and artificially engineered materials. If 3I Atlas exhibits similar, imperceptible, steady propulsion but through a different structural mechanism, porous outgassing rather than reflected pressure, it could indicate that multiple natural pathways can simulate propulsion. Or, as some surmise, it might point towards a more profound, as yet undiscovered pattern among interstellar visitors. The implication is both humbling and exhilarating. The more precisely we measure, the more anomalies come to light. The Hayabusa 2 and OSIRIS-REx missions have demonstrated that microscopic surface characteristics can influence macroscopic motion. ESA's Comet interceptor mission aims to observe one of these bodies in action, potentially an interstellar one, to directly study the invisible physics at play. Upon its success, it could reveal whether 3I Atlas's behavior represents the next stage in the natural evolution of small celestial bodies, or something that defies such classification. In essence, The key to comprehending a massive celestial enigma drifting between the stars might be found within mere milligrams of dust held captive in a laboratory in Japan. Part 14. Frontier Physics. Dark Matter Modified Gravity. Hypotheses regarding spacecraft-like objects. We have explored naturalistic mechanisms and even contemplated the possibility of artificial constructs. However, another category of explanation resides at the very edge of our scientific understanding. Hypotheses that propose forces or interactions that we are only beginning to grasp or have yet to confirm. These concepts necessitate venturing beyond the established boundaries of scientific knowledge and questioning whether the universe harbors phenomena that our current models entirely overlook. Dark matter, modified gravity, exotic particles, and heliospheric boundary effects. Each represent frontiers where observational data is outstripping theoretical frameworks, and where observed anomalies may serve as indicators of new physics. Dark matter stands as one of the paramount unresolved enigmas in contemporary cosmology. Its existence is inferred from observations showing galaxies rotating at speeds that cannot be accounted for by visible matter alone. Galaxy clusters remain gravitationally bound despite a deficit of luminous mass. Gravitational lensing reveals the presence of mass where no visible matter is detected. The evidence overwhelmingly suggests that approximately 85% of the universe's mass is composed of dark matter, interacting primarily through gravity and potentially through forces yet undetected. The precise nature of dark matter remains a profound mystery. Theoretical candidates include weakly interacting massive particles, axions, sterile neutrinos, primordial black holes, and more esoteric possibilities. Despite decades of dedicated research, direct detection of dark matter particles has eluded us, leaving their behavior at small scales and their potential subtle interactions with ordinary matter beyond gravity unknown. Now for the speculative leap. What if dark matter is not uniformly distributed at the scale of our solar system? What if it exists in localized concentrations, streams, or clumps that objects might traverse? The Milky Way is believed to contain dark matter halos and substructures, remnants of smaller galaxies that coalesced with ours in the distant past. Certain models predict the existence of dark matter streams threading through the galaxy, coherent flows of particles moving in unison. If our solar system is currently passing through such a stream, or if 3I Atlas entered the solar system on a trajectory that intersected a region of concentrated dark matter, could this exert a retarding force? The physics becomes nebulous here, as our understanding of dark matter's coupling to ordinary matter beyond gravity is incomplete. If dark matter particles were to scatter off atoms or nuclei, even infrequently, they could transfer momentum. An object moving through a dark matter cloud would experience drag, a force opposing its motion. However, the cross-section for such interactions, if they exist at all, is constrained by experimental data to be extraordinarily small. Dark matter earns its designation precisely because it does not interact strongly. To generate a force on the order of 10 to the -6th astronomical units per day squared on an object weighing millions of kilograms would necessitate dark matter densities far exceeding anything predicted or observed in our galactic vicinity. To quantify this, the estimated local dark matter density near the Sun is approximately 0.3 giga-electron volts per cubic centimeter, which is roughly 100,000 times less dense than interstellar gas. If dark matter particles possess masses around 100 giga-electron volts, and scatter off nuclei with cross-sections approaching current experimental limits, the drag force on a kilometer-sized object would be utterly negligible, orders of magnitude below what is required to explain 3I Atlas's acceleration. To achieve a meaningful drag force, one would require either significantly higher dark matter densities, much larger scattering cross-sections, or some amplifying mechanism. None of these conditions are currently supported by observational evidence. However, what if dark matter interacts via a fifth fundamental force, something beyond gravity and the interactions described by the Standard Model? Some theoretical frameworks propose that dark matter interacts with ordinary matter through novel bosons or via intermediary portals involving Higgs-like fields. If such a force exists and operates over astronomical unit distances, objects moving through dark matter fields could experience accelerations. The challenge lies in the fact that these forces must be exceedingly weak to have escaped detection in laboratory experiments and solar system dynamics thus far, yet sufficiently potent to influence 3I Atlas. Achieving this balance requires highly specific and finely tuned parameters. Another frontier hypothesis involves modified Newtonian dynamics, or MOND, and its relativistic extensions, such as modified gravity theories. MOND was initially conceived to explain galactic rotation curves without invoking dark matter, by proposing that gravity behaves differently at extremely low accelerations. Within the MOND framework, when accelerations fall below a critical threshold of approximately 10 to the negative 10th meters per second squared, gravitational attraction becomes stronger than predicted by Newton's inverse square law. This threshold closely corresponds to the accelerations experienced at the outer regions of galaxies, which explains MOND's efficacy in those contexts. Could MOND or related theories be applicable to 3I Atlas? The object's acceleration is approximately 10 to the negative 6th astronomical units per day squared, which converts to roughly 10 to the negative 8th meters per second squared. While this value exceeds the MOND threshold, it falls within a regime where modified gravity effects might still be relevant, depending on the specific theoretical formulation. If gravity transitions smoothly rather than abruptly at the threshold, there could be residual corrections that manifest as anomalous accelerations. The fundamental issue is that MOND and its variations are designed to account for phenomena at galactic scales, not within individual solar systems. Within our solar system, Newtonian gravity, augmented by general relativity, provides exquisitely accurate predictions. Spacecraft trajectories, planetary orbits, and even the precession of Mercury's orbit align with these predictions to remarkable precision. Invoking modified gravity to explain the motion of a single small body necessitates that the modification is somehow sensitive to the body's specific characteristics, its composition, electric charge, or origin, in a way that does not affect planets or typical asteroids. This presents a formidable challenge and would represent a significant departure from the principle of universality that underpins gravitational physics. A related concept involves the heliospheric boundary and interactions occurring at the periphery of the Sun's influence. The heliosphere is the vast bubble of solar wind and magnetic fields encompassing our solar system, extending approximately 100 astronomical units in the direction of the Sun's galactic motion, and considerably less in other directions. At the heliopause, the boundary where solar wind pressure is counterbalanced by the pressure of the interstellar medium, conditions change abruptly. The density of charged particles shifts, magnetic field orientations reverse, and the environment transitions from being solar-dominated to interstellar-dominated. As an interstellar object, 3I Atlas presumably traversed the heliopause. Could the passage through this boundary have imparted an electric charge, a magnetic moment, or some other property that now causes it to interact anomalously with the solar wind or the heliospheric magnetic field? In principle, this is plausible. The heliopause is a complex region characterized by particle acceleration, magnetic field reconnection, and shock formation. Objects transiting this zone might undergo alterations, acquiring surface charges or embedding magnetic fields. However, even if 3I Atlas became charged or magnetized at the heliopause, the forces it experiences from the solar wind within the inner solar system are contingent upon the magnitude of that charge or magnetization and the prevailing solar wind conditions. As previously discussed, typical solar wind forces are far too weak to account for the observed acceleration. This would require extreme charging, perhaps rendering the object akin to a colossal capacitor, or unusual magnetic properties that interact strongly with the interplanetary magnetic field. There is no observational evidence to support such properties, and positing them without independent verification appears to be adding elaborate justifications. Galactic cosmic rays, which are high-energy particles originating from supernovae and other energetic cosmic events, permeate the heliosphere. Their flux fluctuates with solar activity, and the solar wind modulates their density, reducing their abundance closer to the Sun. Could cosmic rays interact with 3I Atlas in a manner that generates thrust? If the object possesses superconducting materials or peculiar electromagnetic characteristics, it might channel or reflect cosmic rays asymmetrically, thereby creating a net force. This notion is highly speculative, presupposing materials and structures that have never been observed in nature. Furthermore, there is the concept of an interstellar wind composed of exotic particles. What if there exists a population of particles yet to be detected? Not dark matter, but something else entirely. Perhaps sterile neutrinos with slightly altered properties, or hypothetical particles arising from extensions of the Standard Model that stream through the galaxy. If these particles interact with matter more strongly than dark matter but are sufficiently rare to have eluded detection, an object passing through a stream of them could experience drag or thrust. The parameters would need to be extraordinarily precise, common enough to affect 3I Atlas over a 20-day period, yet rare enough not to be evident in other observations, and interacting with just enough force to produce the measured acceleration without any other discernible consequences. All these hypotheses, rooted in frontier physics, share a common characteristic. They necessitate the existence of new, unconfirmed physics to be operative. They are not extensions of well-established theories, but rather speculative additions to our comprehension of the cosmos. This does not inherently render them incorrect. Scientific progress is driven by the proposal and testing of novel ideas. However, it situates them in a distinct category from naturalistic or even artificial explanations. Naturalistic explanations rely on known physical principles applied in innovative ways. Artificial explanations invoke known engineering principles scaled up or implemented by an external agency. Frontier physics explanations, conversely, postulate unknown mechanisms, which renders them more challenging to test and more susceptible to manipulation to fit any observed anomaly. That being said, historical precedent demonstrates that anomalies occasionally do indeed signify new physics. The anomalous precession of Mercury's orbit, which Newtonian gravity could not fully reconcile, ultimately paved the way for the development of general relativity. The rotation curves of galaxies presented anomalies that led to the postulation of dark matter. The accelerating expansion of the universe was an anomaly that gave rise to the concept of dark energy. Not every anomaly represents a groundbreaking discovery. Most are eventually attributed to measurement errors or a misunderstanding of known effects. However, some anomalies are genuine. The critical question is how to differentiate between them. For 3I Atlas, the pathway to validating a frontier physics hypothesis would require multiple lines of corroborating evidence. Firstly, the anomaly must persist and intensify with improved data, thereby ruling out observational artifacts. Secondly, the proposed mechanism must yield testable predictions that extend beyond merely explaining 3I Atlas. For instance, if dark matter-induced drag is a real phenomenon, other small bodies in comparable regions should exhibit similar effects. If heliospheric interactions are responsible for the thrust, correlations with solar wind conditions should be observable, or the effect should be reproducible in laboratory simulations. Thirdly, independent experiments or observations must confirm the underlying physics, such as the direct detection of dark matter interactions, the measurement of modified gravity at relevant scales, or the discovery of the hypothesized exotic particles. None of these crucial steps have yet been undertaken in relation to 3I Atlas. The frontier physics explanations currently remain conceptual frameworks for contemplating possibilities, rather than established scientific theories. While valuable as intellectual exercises that prompt us to question assumptions and probe the frontiers of knowledge, they should not be mistaken for definitive answers. There is also a psychological dimension to frontier physics explanations. They hold a particular appeal due to their exotic nature and transformative potential. If 3I Atlas is indeed evidence of new physics, it would represent an exciting discovery that fundamentally reshapes our understanding of the universe. The temptation exists to prematurely embrace such explanations, to favor the revolutionary over the mundane. The scientific method demands that we resist this temptation, that we exhaust all conventional explanations first, and that we insist on rigorous proof before accepting radical new ideas. Conversely, we must also avoid being so conservative that we disregard genuine signals of new physics. Striking this balance is inherently difficult. In the case of 3I Atlas, the anomalous nature of the data warrants serious investigation, including the exploration of unconventional ideas. However, it is not yet sufficiently compelling to overturn established physics or to justify the construction of new theoretical frameworks based on a single object. Perhaps the most accurate current assessment is that frontier physics hypotheses for 3I Atlas possess a very low probability. Nevertheless, they serve to highlight the limitations of our current knowledge and the inherent possibility that the universe holds surprises. Should 3I Atlas's behavior remain unexplained after an exhaustive investigation of naturalistic and artificial mechanisms, and if similar anomalies begin to accumulate across other objects or systems, then a reconsideration of these frontier ideas would become more justified. Until then, they function as reminders that science is an ongoing process, that the scope of our ignorance vastly exceeds our knowledge, and that maintaining intellectual openness is as vital as upholding skepticism. The dynamic interplay between established physics and speculative frontier ideas defines the essence of the scientific method. We build upon solid foundations, yet remain vigilant for any fissures, any anomalies that defy conventional understanding, and that might point towards something deeper. 3 Atlas represents such an anomaly. Whether it ultimately causes a fundamental shift in our understanding or is revealed to be a peculiar but ultimately natural phenomenon remains to be seen. However, the act of posing these questions, of entertaining even the improbable possibilities, and of designing observations to rigorously test them, is the very engine of scientific advancement. In our concluding section, we will synthesize these insights to offer a forward-looking perspective, outlining key developments to monitor in the coming 12 months, and exploring the broader implications of this ongoing investigation. Part 15. Synthesis and Forward Look. What to monitor in the next 12 months. We have embarked on an extensive journey together, progressing from the initial anomaly of 3I Atlas's unexplained acceleration to naturalistic hypotheses that are strained under scrutiny. We have moved from exotic possibilities of sails and propulsion to the very edges of scientific knowledge concerning frontier physics. We have contextualized this object within the framework of other interstellar visitors, examined the energetic environment of our solar system, and explored the social dynamics that influence scientific interpretation of anomalies. Now, it is time to step back, assess our current understanding, acknowledge what remains unknown, and look ahead to the observations and discoveries that may resolve this mystery or, conversely, deepen it. Let us begin by enumerating what we know with a reasonable degree of certainty. 3 Atlas is traversing the inner solar system along a hyperbolic trajectory, consistent with an interstellar origin. It is exhibiting non-gravitational acceleration characterized by radial and tangential thrust components, designated as A1 and A2, respectively, while demonstrating no measurable acceleration out of the orbital plane. Hence, A3 equals 0. This acceleration has been sustained for approximately 20 days, resulting in a velocity change of about 60 meters per second. Observationally, the object appears as a faint point of light with a magnitude ranging between 14.7 and 14.9. It displays no significant variations in brightness and no discernible coma, tail, or jets in publicly available imagery. Spectroscopic observations, if conducted, have not reported strong emission lines from typical cometary volatile compounds, such as water vapor or carbon monoxide. Now, let us list what remains unknown, and this enumeration is both longer and more consequential. We do not know the precise size or shape of 3I Atlas's nucleus without resolved imaging. Our estimations are currently based on its apparent brightness and an assumed albedo, and the albedo itself is unknown. A dark object would appear faint relative to its actual size, while a bright, reflective object might appear faint simply because it is small. The spectrum of potential sizes encompasses a vast range, spanning numerous orders of magnitude. Our understanding of its mass remains elusive. In the absence of precise measurements for size and density, mass is left entirely unconstrained. Yet, mass is a crucial factor when determining the forces required to achieve the observed acceleration. We are also ignorant of its surface composition, including the specific minerals that might adorn its nucleus, the volatile substances it could harbor, or its reflectivity across various light spectrums. Its rotational state is also unknown. We don't know how rapidly it's spinning, the orientation of its rotational axis, or whether its motion is a stable, steady rotation, or a chaotic tumble. Its thermal characteristics are equally obscure, encompassing how efficiently it absorbs and emits heat, and how heat propagates through its internal structure. Furthermore, its origin story remains a complete mystery, including its parent stellar system, the duration of its interstellar journey through the galaxy, and the environment in which it initially formed. Each of these unanswered questions significantly hinders our ability to differentiate between competing hypotheses. An object that is small and highly reflective would perfectly align with this Sail hypothesis, but would be highly improbable as a naturally occurring comet. Conversely, a large porous body rich in volatiles would better account for natural outgassing processes, but it struggles to explain the absence of a visible coma. A dense, rocky entity containing embedded volatiles might offer an explanation for undetectable venting, but this raises questions about its capacity to retain ice. An object with an unusual composition, perhaps abundant in carbon monoxide or nitrogen, could potentially expel high-velocity gas jets that evade detection, though spectral signatures should still be observable. Until we establish definitive constraints on these properties, our theoretical models are built on unstable foundations. Therefore, what should we be focusing on in the upcoming 12 months? Firstly, and most importantly, trajectory updates. NASA's Jet Propulsion Laboratory's Horizon system continuously refines orbital solutions as new astrometric observations become available. Any alteration in the trajectory of 3I Atlas, any shift in its non-gravitational parameters, or any instance where parameter A3 transitions from 0 to a non-zero value would be highly informative. A change in the observed thrust from planar to three-dimensional would suggest a modification in outgassing geometry, potentially due to different regions of the nucleus rotating into direct sunlight. Consistent planar thrust would strengthen the argument for either precise geometric alignment or active control. Trajectory changes resembling deliberate maneuvers, characterized by sudden velocity adjustments aligning with specific objectives, would constitute extraordinary evidence supporting the propulsion hypothesis. Secondly, coordinated telescope observations. Several major observatories have secured observation time or could propose to observe 3I Atlas. The James Webb Space Telescope, with its exceptional infrared sensitivity, could detect thermal emissions from the nucleus, thereby constraining its size and temperature. It might also be capable of detecting faint molecular emissions in the infrared spectrum that elude ground-based telescopes. These emissions could originate from gases like carbon monoxide, methane, or carbon dioxide, which sublimate readily but emit weakly at visible wavelengths. Large ground-based telescopes equipped with adaptive optics, such as the Keck telescopes in Hawaii, or the Very Large Telescope in Chile, could attempt resolved imaging to discern more than a mere point source, searching for the presence of coma structures, jets, or elongation that might suggest its shape or activity. Spectroscopic analysis across ultraviolet, visible, and infrared wavelengths would contribute to a comprehensive understanding of 3I Atlas's composition and whether it is exhibiting outgassing behavior. Thirdly, photometric monitoring. Continuous measurements of its brightness over several months can reveal its rotation period through variations in its light curve. This monitoring can also constrain its albedo by comparing its brightness at different phase angles and detect any changes in its activity level. A sudden increase in 3I Atlas's brightness could indicate a new outburst, delayed venting triggered by subsurface warming or fragmentation. Conversely, A faster-than-expected fading might suggest a change in its reflectivity or orientation, which would be relevant for evaluating the sail hypothesis. Fourthly, radar observations. Planetary radar systems, such as the Goldstone Solar System radar in California or the Arecibo telescope prior to its collapse, have historically been utilized to observe asteroids and comets, providing direct measurements of their size, shape, spin, and surface roughness. Goldstone remains operational and could potentially detect 3I Atlas if it approaches sufficiently closely and is large enough to generate a detectable signal. Radar observations would provide definitive constraints on its size and reveal whether the object is elongated, spherical, or irregularly shaped. Information critical for distinguishing between hypotheses. Fifthly, AI-driven surveys and archival data analysis. As discussed in Part 2, machine learning algorithms are actively sifting through archival data from sky surveys in search of anomalies. It is plausible that 3I Atlas was imaged months or even years ago during its inbound trajectory, but these observations were not recognized or flagged at the time. Recovering such pre-discovery images would extend the observational timeline, leading to improved orbital solutions and potentially indicating whether the non-gravitational acceleration began gradually or abruptly. AI might also identify similar objects in ongoing surveys, and the existence of a population of such objects would significantly alter our perspective. If 3I Atlas is just one among many, we would be observing a class phenomenon rather than a unique event. Sixthly, solar and heliospheric monitoring. Tracking solar activity, including flares, coronal mass ejections, solar wind conditions, and their temporal relationship to any observed changes in 3I Atlas's behavior, could reveal correlations. If the object's acceleration intensifies or diminishes in response to solar events, this would suggest environmental coupling. Conversely, if it remains independent of solar variations, this would argue for intrinsic mechanisms, either venting driven by internal processes or propulsion. Seventh, theoretical advancements. Papers are undoubtedly being authored at this moment, modeling various scenarios and testing whether specific compositions or structural configurations can replicate the observed data. Publications in esteemed journals such as Nature, Science, the Astrophysical Journal, or Icarus will present competing interpretations, which will then be debated by the scientific community. While consensus may eventually emerge, or the debate might persist unresolved, the theoretical work will undoubtedly refine our understanding of what is scientifically plausible and what is not. Eighth, mission proposals. While unlikely, it is not impossible that space agencies might expedite a mission to intercept or observe 3I Atlas at closer range. Interstellar objects travel at high velocities and are challenging to reach. However, if 3I Atlas is deemed sufficiently significant, a flyby mission utilizing existing spacecraft or a rapid response probe could be proposed. The European Space Agency's Comet interceptor mission is designed for such opportunities, though its launch is scheduled for the late 2020s. Nevertheless, the prospect of close-up observation, even by a small CubeSat, would provide conclusive answers. Now, let us explore potential scenarios for how this situation might unfold over the next year. Scenario A. A natural explanation is confirmed. High-resolution imaging or spectroscopy reveals a faint coma or jets that were previously below the detection threshold. These jets are found to be aligned in such a way, due to the nucleus's spin and shape, that they produce a net thrust confined to the orbital plane. The composition is determined to be rich in supervolatiles like carbon monoxide, accounting for the high-velocity venting and minimal dust production. A detailed model incorporating all these factors successfully reproduces the observed acceleration, thereby solving the mystery. 3 Atlas would then be classified as a remarkable example of an unusual but fundamentally natural interstellar comet, teaching us that our assumptions about cometary behavior were perhaps too restrictive. The object would enrich our understanding but not revolutionize it. Scenario B. An exotic explanation gains credibility. Photometric observations across multiple wavelengths indicate an unusually high albedo, approaching 90 or 100%, significantly exceeding that of any known natural comet. Analysis of the phase curve suggests that 3I Atlas reflects light like a smooth, flat surface, rather than a rough, irregular celestial body. Thermal measurements indicate a very low mass, implying an extremely low density that is inconsistent with solid ice or rock. Collectively, these findings point towards a thin, lightweight structure, akin to a sail. The scientific community would then engage in debate regarding whether such a structure could form naturally, perhaps as a frozen sheet of volatiles in interstellar space, or if it represents artificial construction. No immediate consensus would be reached, but the sail hypothesis would emerge as the leading explanation, ushering in a new era in the study of interstellar objects and prompting profound questions about whether we are observing technology, either ours or from another civilization, adrift between the stars. Scenario C. No definitive resolution is achieved. Additional observations enhance the constraints on the object's properties, but do not decisively favor any single hypothesis. The coma remains absent or barely detectable. Albedo measurements prove inconclusive. The non-gravitational parameters continue to be perplexing. 3 Atlas fades as it exits the inner solar system, becoming too faint for detailed analysis. The object would remain an enigma, catalogued as an anomaly that could not be explained with the available data. Years later, with the advent of improved instruments or the discovery of more similar objects, scientists might revisit the observations of 3I Atlas. However, in the short term, it would represent an unsolved puzzle, a frustrating reminder of the limitations of current observational capabilities. Each scenario carries distinct implications. Scenario A, the natural resolution, would be scientifically most satisfying in certain respects, demonstrating that nature is more varied and stranger than we previously comprehended, yet confirming the fundamental soundness of our physical models. It would encourage observers to scrutinize future interstellar objects more meticulously, to avoid assuming that comets always exhibit visible venting, and to anticipate the unexpected. Scenario B, the exotic resolution, would be transformative. If 3I Atlas is indeed a sail, whether natural or artificial, it would compel us to broaden our conception of what exists within the galaxy, how matter self-organizes on vast scales, and potentially whether intelligence is a rare or common phenomenon. The ramifications would extend into philosophy, astrobiology, and technology. Scenario C, the unresolved mystery, is the least gratifying but perhaps the most realistic. Scientific progress often proceeds slowly, constrained by resources, technological advancements, and the inherent difficulty of observing distant, faint objects. Not all questions are answered promptly, and some remain open for decades. Beyond the immediate resolution of this case, 3I Atlas raises broader questions about our methodologies for searching for and interpreting anomalies. This object was detected because our monitoring systems are sufficiently advanced to identify minor deviations from gravitational orbits, and because the astronomical community remains vigilant for interstellar visitors. However, how many anomalies do we overlook? How many objects pass through unnoticed due to their faintness, their subtle behavior, or our failure to observe them at the appropriate wavelengths? The answer is undoubtedly numerous. The cosmos is immense. Our surveys cover only a fraction of it at any given moment, and small celestial bodies are notoriously difficult to track. Enhancing our detection capabilities, constructing larger telescopes, deploying more sensitive instruments, and utilizing AI to analyze vast datasets all contribute to expanding our observational reach. Each improvement increases the probability of discovering more objects similar to 3I Atlas, or even more peculiar ones. With each new discovery, our classification of what constitutes normal expands. What once seemed impossible gradually becomes possible, and what appeared unique becomes part of a recognizable pattern. This is the inherent trajectory of scientific advancement, progressing from ignorance to partial understanding, and ultimately to deeper comprehension, always subject to revision based on new evidence. There is also a meta-level question concerning how science addresses extraordinary phenomena. When confronted with an anomaly that challenges established assumptions, how do we strike a balance between skepticism and open-mindedness? Excessive skepticism risks dismissing genuine discoveries prematurely, while excessive openness can lead to wasted efforts on unsubstantiated claims and pseudoscience. The peer review process, public discourse, and replication of results serve as safeguards, though they are not infallible. Careers, funding, and reputations are at stake, creating social pressures that can influence objectivity. 3 Atlas tests these dynamics. Natural hypotheses represent the conservative approach, offering explanations that fit within existing frameworks and are predisposed for community acceptance. Exotic hypotheses are more speculative, requiring more substantial evidence and facing higher hurdles for publication. Frontier physics hypotheses are the riskiest, proposing novel mechanisms that most scientists consider improbable. Nevertheless, all 3 categories warrant consideration and evaluation based on their merits against the available data. The challenge lies in maintaining this equilibrium, avoiding both the premature dismissal of ideas and their uncritical acceptance. For those observing from outside the scientific community, 3 Atlas serves as a potent reminder that the universe is replete with surprises, that our current knowledge is incomplete, and that the boundaries of the known are precisely where the most fascinating discoveries are made. It also underscores that science is fundamentally a human endeavor, shaped by the individuals who practice it, with all their creativity, biases, passions, and limitations. We should therefore celebrate the progress science achieves while acknowledging its inherent imperfections. As we conclude this exploration, here is a question to ponder. Are we observing not merely a comet, but a signal of something novel entering our solar neighborhood, something that defies our existing classifications, something that compels us to conceive of larger and more unconventional possibilities? Perhaps 3 Atlas is simply an unusual but ultimately natural comet. Or perhaps it is something else entirely, a sail, a probe, a fragment of extraterrestrial engineering, or an embodiment of physics beyond our current grasp. The data does not yet provide a definitive answer, but the very act of posing these questions rigorously and seriously is itself significant. The coming 12 months will bring forth new observations, analyses, and debates. Stay informed. Follow the updates from JPL Horizons. Look for research papers on 3 Atlas from scientists. Listen to the ongoing discussions within the astronomical community. The narrative is still unfolding, and you are a witness to its real-time development. Science at its finest is a collective human endeavor to comprehend reality, and mysteries like 3 Atlas are precisely why that effort is so vital. We stand at a precipice, gazing out at a visitor from the stars, attempting to decipher its secrets. It traverses the darkness silently, defying our expectations, whispering that the cosmos holds far more than we have yet imagined. Whether it represents a cosmic anomaly or a cosmic message, time and continued observation will reveal the truth. For now, we observe, we wonder, and we wait, acknowledging that the universe has surprised us before, and undoubtedly will again. And with each surprise, we move one step closer to comprehending our place within the infinite expanse. The anomaly presented by 3 Atlas is not merely a scientific puzzle. It is an invitation to scrutinize more intently, to contemplate more profoundly, and to maintain humility in the face of the vastness of our undiscovered knowledge. And this, perhaps, is its most significant lesson.